Welcome to the channel. If you are interested in space, science, deep questions, and the real nature of the universe, you are in the right place. Here we go beyond simple facts and explore ideas that change how you see reality itself. Before we begin, make sure to subscribe to the channel. New videos are released regularly, and subscribing helps you not miss the next journey into the unknown. If you enjoy thoughtful, high-quality content, a like is the best way to support the channel and help this video reach more people who are curious about the universe. And now, let us begin. The moon and the illusion of a perfect place for life. For most of human history, the moon was never treated as a scientific problem. It was a symbol, a lamp in the night sky, a silent companion for travelers, poets, and lovers. We learned to see it as something familiar and harmless, a pale disk that rises and sets with comforting regularity. But for science, the moon is not a decoration. It is a question, and more importantly, it is a contradiction. From the point of view of planetary science, the moon represents one of the largest unused territories near Earth. Its surface area is about 38 million square kilometers. That is almost as much land as Asia and Africa combined. A continent-sized world hangs just 3 days away from us in space, completely empty. No oceans, no forests, no atmosphere worth mentioning. Just rock and dust. And here comes the paradox. The moon is located in one of the most privileged regions of the solar system. It orbits the Earth, and the Earth orbits the Sun at a distance that astronomers consider nearly ideal. This region is often called the habitable zone, or more poetically, the Goldilocks zone. Not too hot, not too cold, just right for liquid water to exist. Since the moon shares almost the same orbital distance from the Sun as Earth, it technically sits at the same cosmic table. The same sunlight reaches it. The same energy flows across its surface. Yet the bowl, in front, the moon is empty. No rivers flow there. No rain has ever fallen. No stars reflect the sunlight. How can two ring worlds, born in the same region of space, under the same star, end up so radically different? Why did Earth become a living planet, while the moon turned into a frozen desert of stone? This question is not just philosophical. It cuts directly into how we search for life beyond our planet. Every headline that claims scientists have discovered a second Earth somewhere in the galaxy relies on one core assumption. Distance from the star equals potential for life. The moon quietly laughs at this assumption. To understand why, we need to begin with the foundation of modern astrobiology. The concept that dominates discussions about alien worlds, the habitable zone. The idea sounds simple. Around every star, there exists a region where conditions might allow liquid water to exist on the surface of a planet. Too close, water boils away. Too far, and it freezes solid. Somewhere in between lies a narrow ring where water could remain liquid. Since water is essential for all known life, this zone became the holy grail for planet hunters. The metaphor comes from a children's fairy tale. Goldilocks tastes 3 bowls of porridge. One is too hot, one is too cold. The third is just right. In planetary terms, Mercury is too hot. Mars and Pluto are too cold. Earth appears to sit perfectly in the middle. Because the moon orbits Earth, it technically shares this same sweet spot. From the perspective of sunlight alone, it should not be a frozen wasteland. It should at least have had a chance. To see why this expectation fails, we must look at where the concept of the habitable zone came from, and what it truly means. The term did not emerge from modern space telescopes. Its roots go back to the mid-20th century. In the early 1950s, scientists began thinking seriously about the relationship between stars, planets, and life. In 1953, the idea of an ecosphere was introduced, describing the region around a star where life could potentially exist. Later, in 1959, an astrophysicist named Su Huang refined the concept by linking it to the lifetime of a star. The most influential definition appeared in 1964, when Stephen Dole published a book called Planets for Man. He attempted to calculate which stars could host planets suitable for human life. In the 1990s, these ideas were transformed into a rigorous scientific framework by James Casting and his colleagues. To this day, Casting's model remains the standard reference. And here is where the first disappointment arrives. The scientific definition of the habitable zone is far more modest than most people realize. It does not promise life. It does not even promise water. It simply defines a region where a planet with sufficient atmospheric pressure could maintain liquid water on its surface. The key word is could. The habitable zone is not a guarantee. It is a permission slip from physics. A statement that the laws of thermodynamics do not immediately forbid liquid water. Nothing more. Imagine buying a house. The real estate agent tells you the climate is perfect. No extreme heat. No brutal winters. Does that mean you will live comfortably? Of course not. If the house has no roof, no walls, and no insulation, you will freeze no matter how gentle the weather outside may be. The habitable zone is the neighborhood. The planet itself is the house, and the moon a house with no walls. To understand just how severe this problem is, we need to look at the numbers. Earth orbits the Sun at an average distance of about 149 million kilometers. Astronomers call this distance one astronomical unit. The Moon orbits Earth, sometimes slightly closer to the Sun, sometimes slightly farther away. But on cosmic scales, this difference is meaningless. For sunlight, there is essentially no distinction between hitting the Pacific Ocean or a crater on the Moon. A vast amount of energy reaches the Earth-Moon system. There is a value called the solar constant. It measures how much energy from the Sun arrives at a square meter facing directly toward it. That value is about 1,361 watts per square meter, roughly the power of a strong microwave oven, continuously pouring down on every exposed surface. At first glance, it seems like more than enough energy to support warmth and life. So why does this same sunlight create tropical beaches on Earth and a deadly vacuum on the Moon? Many people immediately answer that the Moon has no atmosphere. That is true, but it is only part of the story. The absence of an atmosphere is not the original cause. It is the consequence. Before we deal with atmosphere, we must deal with temperature. In physics, there is a concept known as the equilibrium temperature of a black body. It describes the temperature an object would have if it absorbed sunlight and radiated heat back into space without any insulating layer, such as an atmosphere. If we calculate this temperature for Earth, using its distance from the Sun and basic physical laws, we get a surprising result, about -18 degrees Celsius. But Earth's actual average surface temperature is around +15 degrees Celsius. That is a difference of more than 30 degrees. This difference is created by the atmosphere. Earth's atmosphere acts like a thermal blanket. Sunlight passes through it and warms the surface. The surface then radiates infrared heat back upward. But greenhouse gases trap a significant portion of this heat, preventing it from escaping into space. These extra degrees make the planet truly habitable. Now imagine removing the blanket completely. That's the Moon. The Moon has no global atmosphere to speak of. It behaves almost exactly like a naked black body, with only one small correction factor called albedo, which describes how much light a surface reflects. Here we encounter another illusion. When we look at the full moon in the night sky, it appears bright and white. It seems almost luminous. But this is a trick of contrast. Against the blackness of space, even a dark surface looks bright. In reality, the moon is surprisingly dark. Its average albedo is only about 12%. That is roughly the same reflectivity as worn asphalt. Earth, by comparison, reflects about 30% of incoming sunlight thanks to clouds, ice, and oceans. The dark lunar soil, called regolith, absorbs most of the sunlight that hits it. During the lunar day, when the sun stands high above the surface, temperatures soar to about 127 degrees Celsius, hotter than boiling water, hotter than the hottest desert on Earth. In such conditions, liquid water cannot exist for even a moment. It would instantly boil away. Then arrives. A lunar night lasts about 2 Earth weeks. Without an atmosphere to retain heat, the surface radiates its energy straight into space. Temperatures plunge to around -173 degrees Celsius. The result is a temperature swing of nearly 300 degrees. These extreme oscillations happen precisely in a region. According to the habitable zone concept, conditions should be comfortable, This alone should make us cautious when we hear claims about newly discovered Earth-like planets. Telescopes such as Kepler or James Webb can tell us how far a planet is from its star. They can estimate its size, but until we understand its atmosphere, its magnetic field, and its internal structure, we have no idea whether it is a paradise or just another silent rock. There is another subtle factor often overlooked when discussing habitability: volatile substances. For a planet to become alive, it is not enough to sit at the right distance from a star. Aids building materials. Carbon, nitrogen, elements that can form atmospheres and oceans. Imagine preheating an oven to the perfect temperature, then realizing you forgot to put any ingredients inside. The oven does not bake a cake. It only creates the conditions for baking. The moon is an empty oven. Earth and the moon formed in the same region of the early solar system were born from the same swirling disk of dust. They had access to the same chemical buffet. Yet Earth collected vast oceans and a thick atmosphere, while the moon ended up almost completely dry. For a long time, scientists blamed gravity. The moon is smaller, so it could not hold on to gases. This explanation is correct, but incomplete. There are moons in the solar system even smaller than our moon that contain enormous amounts of water. Enceladus, orbiting Saturn, and Europa, orbiting Jupiter, are tiny worlds with global oceans hidden beneath ice. They exist far outside the traditional habitable zone, in the realm of deep cold. So here is the deeper contradiction. In the cold outskirts of the solar system, small bodies can hold water. In the warm inner region, a relatively large moon cannot. This suggests that the habitable zone, as traditionally defined, is a concept deeply biased by Earth itself. We look for worlds that resemble our own, ignoring alternative paths to habitability. But to truly understand the moon's fate, we need to dig deeper than temperature and distance. We need to ask a more fundamental question. Did the moon ever have an atmosphere at all, or was it born dead? That question takes us back billions of years, to a time when the solar system was young, violent, and unstable. To answer it, we must return to the moment of the moon's birth itself. And that story begins not with gentle accumulation, but with fire, collision, and catastrophe. In the next part, we will travel 4.5 billion years into the past, to the event that shaped the moon's destiny before it ever had a chance to live by fire. The giant impact and a world that never had a chance. To understand why the moon is empty, airless, and hostile, we must abandon the idea that it was ever meant to resemble Earth. The moon did not fail at becoming a living world. It was never given a fair opportunity to begin with. Its fate was sealed at birth. The story starts around 4.5 billion years ago, when the solar system was still forming. At that time, planets were not peaceful spheres quietly settling into stable orbits. They were unfinished bodies colliding, fragmenting, merging, and reshaping each other in a chaotic environment filled with debris. Earth itself was still young. Its surface was molten in places. Volcanoes were common, impacts were frequent, and among the many bodies sharing the inner solar system was another protoplanet, roughly the size of Mars. Scientists call it Theia. Theia did not gently pass by Earth. It struck it. This collision was not a small impact. It was a planetary-scale catastrophe. Theia slammed into the early Earth at a shallow angle, releasing an unimaginable amount of energy. Enough to melt vast portions of both bodies. Enough to eject enormous quantities of material into space. Enough to rewrite the future of two worlds in a single event. From this debris, the moon was born. This is known as the giant impact hypothesis, and today it is the leading explanation for the moon's origin. It explains the moon's size, its orbit, and most importantly, its chemical composition. The material that formed the moon did not come from Earth's deep interior, where heavy elements concentrate. It came mostly from the outer layers of Earth and from Theia itself. These layers were already depleted in volatile substances. Volatiles are elements and compounds that evaporate easily. Water, carbon dioxide, nitrogen, ammonia. These substances are essential for atmospheres and oceans, but they are also fragile. Heat drives them away. The giant impact generated temperatures of several thousand degrees Celsius. In such conditions, volatile compounds do not survive. They escape into space. The The debris disk that formed around Earth after the impact was not a cool cloud of dust gently assembling into a moon. It was a glowing ring of molten rock and vapor. For hundreds to thousands of years, Earth was surrounded by a disk of incandescent material, the moon, from this disk. This single fact explains more about the moon's emptiness than any later process. The moon was assembled from material that had already been stripped of most of its water and gases. It was born dry. Evidence for this can be found today in lunar samples. When Apollo astronauts brought back rocks from the moon, scientists were surprised by how similar they were to Earth's mantle and how poor they were in volatile elements. The isotopic ratios of oxygen in lunar rocks are nearly identical to those on Earth, something not seen in any other body in the solar system. This tells us that the moon is not a captured object. It is not an alien world that wandered into Earth's orbit. It is a piece of Earth's history that was violently torn away and reshaped. But similarity does not mean equality. The Earth recovered from the impact. The moon did not. Earth's gravity was strong enough to hold onto much of its atmosphere, or to rebuild it quickly through volcanic outgassing. Earth's interior remained hot and active, driving plate tectonics and recycling material between surface and mantle. This geological activity played a crucial role in stabilizing climate and preserving water over billions of years. The moon, by contrast, cooled rapidly. Its smaller size meant a smaller internal heat reservoir. Within a relatively short time on geological scales, the moon's interior solidified. Volcanic activity declined. The processes that could have released gases to form an atmosphere slowed, and then largely stopped. For a brief window, the moon may have had a thin atmosphere. Studies suggest that during periods of intense volcanic activity, especially around 3 to 4 billion years ago, the moon may have temporarily possessed an atmosphere composed of gases like carbon monoxide, sulfur dioxide, and water vapor. But this atmosphere would have been extremely tenuous, more like a transient haze than a protective blanket. And it did not last. The moon's gravity is only about 1/6 that of Earth. This makes it much harder to retain gas. Molecules in an atmosphere are constantly moving. Some move faster than others. If a molecule reaches escape velocity, it is gone forever. At lunar gravity, even relatively heavy molecules can escape over time, especially when heated by sunlight or energized by radiation. And here the sun enters the story again, not as a source of life, but as an agent of erosion. The young Sunday was far more violent than it is today. In its early stages, it emitted intense ultraviolet radiation and powerful solar winds. Charged particles streamed outward at high speed, slamming into planets and moons. Earth survived this phase because it had a strong magnetic field. The moon did not. A magnetic field acts as a shield. It deflects charged particles, preventing them from directly striking the atmosphere. Earth's magnetic field arises from its molten, rotating iron core. The moon, being smaller, lost its internal dynamo relatively early. For a time, the moon may have had a weak magnetic field, but it faded quickly. Once it was gone, the solar wind had a clear path. Any atmosphere the moon managed to produce was stripped away molecule by molecule. Water vapor was broken apart by ultraviolet radiation. Hydrogen escaped into space. Oxygen either escaped or reacted with surface rocks. Nitrogen and carbon compounds followed. This process did not require a dramatic event. It did not need a massive explosion or a sudden catastrophe. It was slow, relentless, and irreversible. The moon was exposed. Even worse, because the moon orbits Earth, it periodically passes through Earth's magnetotail, a long extension of Earth's magnetic field stretched away from the sun. For a time, scientists thought this might help protect the moon, but measurements have shown that this interaction can actually accelerate atmospheric loss by energizing particles rather than shielding them. By the time Earth was developing stable oceans and a thick atmosphere, the moon had already become what it largely is today. A vacuum wrapped around a frozen record of early solar system history. This is why the moon is such a valuable scientific object. Its surface is ancient. Without atmosphere, wind, rain, or plate tectonics, lunar craters remain for billions of years. The moon is a fossil, preserving a timeline Earth erased through constant renewal. But this same preservation is also a sign of death. A living planet must change. It must cycle material. It must renew itself. Stagnation on a planetary scale is not stability. It is decay. The moon never developed the internal engines required for long-term habitability. No plate tectonics, no long-lived volcanism, no magnetic field, no thick atmosphere. Even if water had somehow arrived later through comet impacts, it would not have stayed. Most of it would have sublimated directly into space. A small fraction be trapped in permanently shadowed craters near the lunar poles, where sunlight never reaches. There, temperatures are so low that ice can survive for billions of years. These polar ice deposits often fuel optimistic headlines about lunar bases and water resources. But they are not signs of a living world. They are signs of a freezer, a place so hostile that water can only survive where the sun never shines. This brings us back to the illusion of the habitable zone. The moon sits comfortably within it, yet remains lifeless. Distance from a star is not destiny. Birth matters. Composition matters. Gravity matters. Magnetic fields matter. Geological activity matters. Timing matters. The moon lost the lottery on nearly every count. In the next part, we will focus on one of the most underestimated factors in planetary survival: gravity. Not as a force that keeps us on the ground, but as a gatekeeper that decides whether a world can ever hold onto air, water, and the ingredients of life. Gravity as a gatekeeper. Why size decides a world's fate. When people think about gravity, they usually imagine weight. How heavy something feels, how high you can jump, strongly a planet pulls you toward its surface. But on a planetary scale, gravity plays a far deeper role. It is not just a force of attraction, it is a filter, a gatekeeper that decides whether a world can keep the ingredients of life or lose them forever. The moon's failure to become a living world cannot be understood without understanding gravity at this level. Every planet or moon exists in a constant struggle with space itself. Atoms and molecules on the surface are always in motion. Heat gives them energy. Radiation excites them. Collisions push them in random directions. An atmosphere is not a static shell. It is a dynamic swarm of particles, endlessly bouncing, colliding, rising, and falling. Gravity is the only thing that keeps this swarm from leaking away. To escape a world, a particle must reach a specific speed called escape velocity. This is the minimum speed required to break free from the gravitational pull and never fall back. On Earth, escape velocity is about 11.2 kilometers per second. On the Moon, it is only about 2.4 kilometers per second. That changes everything. At any given temperature, gas molecules move at a range of speeds. Some move slowly. Some move fast. Even at modest temperatures, a small fraction of molecules will always be moving fast enough to escape a weak gravitational field. Over time, those losses add up. On Earth, gravity is strong enough to hold on heavy gases like nitrogen and oxygen for billions of years. Lighter gases like hydrogen and helium can escape, which is why Earth does not have a hydrogen atmosphere. But the gases that matter for life remain trapped. On the Moon, even heavier molecules struggle to stay. At lunar gravity, nitrogen, carbon dioxide, and water vapor are only marginally bound. Add sunlight, ultraviolet radiation, and energetic particles from the sun, and escape becomes inevitable. The Moon does not need a violent event to lose its atmosphere. It only needs time, and time always wins. This is why gravity must be considered before atmosphere, before water, and before habitability. Without sufficient gravity, everything else is temporary. Mars provides a powerful comparison. Mars is far larger than the Moon. Its gravity is about 38% of Earth's. That is more than double the Moon's. Yet Mars still lost most of its atmosphere. Today it has a thin shell of carbon dioxide, less than 1% of Earth's atmospheric pressure. Evidence suggests that early Mars had rivers, lakes, and possibly shallow seas. It had volcanoes, weather, and a thicker atmosphere. But over billions of years, its smaller size worked against it. Its core cooled, its magnetic field weakened. The solar wind stripped its atmosphere away. If Mars struggled to hold onto air, the Moon never stood a chance. This allows us to define an informal, but powerful rule of planetary science. Size matters more than location. A small world in the perfect orbital zone will lose its atmosphere. a large world far from its star can keep internal heat and liquid water under ice. Gravity determines whether a planet can play the long game. For the Moon, the consequences were immediate and permanent. As soon as the Moon cooled after its violent birth, any gases released from its interior face simple choice: fall back to the surface or escape into space. With such low gravity, escape slowly but surely dominated. Even impacts did not help. Comets and asteroids have delivered water and volatile compounds to many bodies in the solar system. Earth gained a significant portion of its water this way. The Moon was also bombarded, especially during the period known as the Late Heavy Bombardment. When an icy comet strikes a planet with strong gravity and an atmosphere, some of its water can survive. It vaporizes, mixes with the atmosphere, rains out, and becomes part of the hydrological cycle. On the Moon, the same impact produces a brief cloud of vapor that expands rapidly and escapes. Most of the delivered water is lost within hours or days. Only a tiny fraction becomes trapped in cold regions near the poles. This means the Moon is not just dry by origin. It is actively hostile to water. Gravity also controls surface pressure. Without pressure, liquid water cannot exist. At the Moon's surface, atmospheric pressure is essentially zero. Water does not melt. It sublimates. It goes directly from solid to vapor. Even if the Moon were suddenly flooded with ice, it would not form oceans. It would slowly disappear into space. Gravity alone would already be enough to disqualify the Moon as a candidate for long-term habitability. But it does not act alone. It works in combination with another invisible but critical factor: magnetism. A planet's magnetic field is often described as a shield, and that description is accurate but incomplete. It is not only a shield against radiation. It is a stabilizer of atmospheres over geological time. On Earth, the magnetic field deflects most charged particles from the solar wind. These particles carry energy that would otherwise strike the upper atmosphere, heating it and giving gas molecules extra speed. Without this shield, atmospheric loss accelerates dramatically. Mars lost its magnetic field early in its history. Once it did, its atmosphere began to erode far more rapidly. Being even smaller, lost its magnetic field even sooner. For a brief time after its formation, the Moon may have possessed a weak magnetic field. Lunar rocks show traces of magnetization, suggesting an early dynamo. But this field was short-lived and weak compared to Earth's. Once it faded, the Moon was fully exposed. Solar wind particles slammed directly into the surface, embedding themselves in the regolith, sputtering atoms into space, and eroding any remaining gases. Over billions of years, this process transformed the Moon into the airless body we see today. Gravity decided how hard it would to hold onto an atmosphere. Magnetism decided how aggressively space would try to take it away. The Moon lost on both fronts. This realization has profound consequences beyond our solar system. When astronomers discover a planet in the habitable zone of a distant star, they often celebrate. But without knowing its mass, density, and its magnetic field, that celebration is premature. A planet can be perfectly positioned and still be dead. The Moon proves this with brutal clarity. It sits next to Earth, bathing in the same sunlight, sharing the same region of space, and yet it is fundamentally incapable of sustaining life on its surface. Not because of bad luck, but because physics forbids it. In the next part, we will examine the invisible enemy that finished the job: solar radiation and stellar wind. Forces that do not merely warm worlds, but actively dismantle them, particle by particle, until nothing remains but stone and memory by solar wind and radiation. How stars slowly erase worlds. Gravity and magnetism decide whether a planet can defend itself. Radiation decides how aggressively the universe will attack. The Moon did not lose its atmosphere in a single dramatic event. It was not stripped bare by one colossal storm. Its destruction was slower, quieter, and far more ruthless. It was dismantled atom by the constant presence of its own star. To understand this process, we need to change how we think about sunlight. The sun is not just a source of warmth and light. It is a particle accelerator. Every second emits a continuous stream of charged particles known as the solar wind. This wind is made mostly of protons and electrons, traveling at speeds of hundreds of kilometers per second. Embedded within it are magnetic fields carried outward from the sun itself. On Earth, this invisible storm collides with our magnetic field and is largely deflected. The result is a protective bubble called the magnetosphere. Most of the solar wind flows around it, barely touching the atmosphere below. Only near the poles do some particles leak through, producing auroras. On the moon, there is no such shield. When the solar wind reaches the moon, it strikes the surface directly. This has consequences far beyond what most people imagine. When high-energy particles collide with surface atoms, they transfer momentum. Some atoms are knocked free entirely. This process is called sputtering. Over time, sputtering ejects atoms from the surface into space. Oxygen, sodium, potassium, and other elements are constantly being blasted away. This is not speculation. We have measured it. Orbiting spacecraft have detected a faint cloud of atoms surrounding the moon. This is called the lunar exosphere. It is not an atmosphere in any meaningful sense. It is a ghost, a constantly replenished, constantly escaping collection of atoms temporarily hovering above the surface before vanishing into space. Each atom survives only hours or days before it is lost. This is what remains after billions of years of exposure. Radiation adds another layer of destruction. Ultraviolet radiation from the sun is energetic enough to break molecular bonds. When water vapor is exposed to ultraviolet light, it splits into hydrogen and oxygen. Hydrogen, being extremely light, escapes almost instantly from weak gravity. Oxygen may linger briefly, but without protection, it too is eventually lost or locked into surface minerals. This means that even if the moon had managed to collect water early in its history, sunlight itself would have worked against it. The sun does not merely illuminate, it dismantles, and the early Sunday was far worse. Young stars are violent. In their first billion years, they rotate faster, generate stronger magnetic fields, and produce far more intense radiation and stellar winds. The early sun bombarded the inner solar system with levels of radiation that would be devastating today. Earth endured this phase because it had three critical advantages: strong gravity, a long-lived magnetic field, and a massive reservoir of water and gases that could absorb damage and recover. The moon, none of these. During the first few 100 million years after its formation, the moon was exposed to an onslaught of radiation precisely when it was most vulnerable. Any early atmosphere it might have possessed was torn apart quickly. Any surface water was destroyed or lost. Any hope of stability was erased before it could take hold. This is why the moon today is not just dry, but chemically altered. The lunar soil is saturated with solar wind particles. Hydrogen ions from the sun embed themselves into the regolith. Some react with oxygen and minerals to form trace amounts of hydroxyl and water. This process produces tiny quantities of water on the surface, especially at high latitudes. This discovery led to optimistic headlines about water on the moon, but this water is not evidence of habitability. It is evidence of exposure. The moon is so unprotected that even the solar wind leaves fingerprints on its surface. The same process that creates a few molecules of water also strips away everything else. Radiation also affects temperature in subtle ways. Without an atmosphere, there is no redistribution of heat, no winds, no clouds, no oceans to absorb energy. The sun heats only what it touches. When it moves on, the heat is gone. This creates a surface environment that is not merely extreme, but unstable. Any attempt to build long-term structures, ecosystems, or even sustain chemical complexity is constantly reset by thermal stress. Materials expand and contract violently. Chemical reactions stall. Organic molecules break apart. From the perspective of life, the lunar surface is not just hostile. It is actively destructive. This brings us critical insight. The habitable zone does not protect worlds from their stars. It only sets a temperature range where protection might matter. Without gravity and magnetism, proximity to a star becomes a liability, not an advantage. The moon demonstrates this perfectly. It sits in an ideal thermal location, yet suffers from constant radiation damage. In contrast, moons like Europa and Enceladus orbit far from the sun, outside the classical habitable zone, yet manage to preserve vast oceans beneath thick ice. Their water survives precisely because it is hidden and protected. This flips our intuition upside down. Warmth without protection is dangerous. Cold with protection can be safe. The moon chose warmth and paid the price. By now, a pattern should be clear. The moon did not miss a single requirement for life. It missed many, and each failure amplified the others. Violent birth removed volatiles. Low gravity prevented recovery. Loss of magnetism allowed radiation in. Solar wind stripped what remained. Temperature extremes finished the job. None of these factors alone would necessarily doom a world. Together, they are decisive. In the next part, we will address a question that naturally follows. If the moon is so hostile on the surface, why do scientists keep talking about water, ice, and potential bases near its poles? What exactly is hidden in the eternal shadows, and why that discovery is both fascinating and deeply misleading? Ice in eternal shadow. Why water on the moon changes nothing. By now, the moon may seem completely closed to hope, and yet, again and again, headlines appear claiming the opposite. Scientists announce the discovery of water on the moon. News articles speak of ice reserves, plans for permanent lunar bases resurface. The narrative shifts from impossibility to opportunity. This is where misunderstanding reaches its peak. Yes, there is water on the moon, but understanding where it is, how it exists, and what it means is essential. Because this water is not a sign of habitability, it is evidence of extreme hostility. To see why, we must travel to the most unusual places on the moon. The lunar poles. Unlike Earth, the moon has almost no axial tilt. Earth is tilted by about 23 degrees, which gives us seasons. The moon's tilt is only about 1.5 degrees. This means the sun never rises high above the horizon at the lunar poles. As a result, there are craters near the north and south poles whose interiors have not seen sunlight for billions of years. These regions are called permanently shadowed regions. Inside these craters, temperatures drop to astonishing levels, as low as -230 degrees Celsius. Colder than Pluto, colder than most places in the solar system. In such cold, water does not melt. It does not even sublimate. It becomes locked in place like a fossil in ice. This is where water survives. Not in oceans, not in soil, not in the open. Only in darkness so complete and cold that sunlight never reaches it. This fact alone should change how we interpret the discovery. On Earth, water is everywhere because the environment supports it. On the moon, water exists only where the environment is so hostile that even heat cannot reach. The water found in these craters comes from multiple sources. Some was delivered by comet impacts. Some may have been produced by chemical reactions triggered by solar wind hydrogen interacting with oxygen in lunar minerals. Some may be ancient, trapped since the early solar system, but regardless of its origin, its survival depends on one condition: eternal shadow. If this ice were exposed to sunlight for even a short time, it would disappear. This is why water on the moon does not contradict anything we have learned so far. It confirms it. The moon cannot support water under normal conditions. Only under the most extreme protection does water persist. This distinction matters greatly when people talk about lunar colonization. Water is often described as the key resource. It can be used for drinking, oxygen, and fuel. Split into hydrogen and oxygen, it becomes rocket propellant. Ice at the poles sounds like a solution. In reality, it is a technical nightmare. These permanently shadowed craters are among the most difficult environments imaginable. They are pitch black. No sunlight means no solar power. Temperatures are so low that most materials become brittle. Lubricants freeze. Electronics struggle. Human activity becomes dangerous. To access the ice, machinery must operate in darkness at temperatures far below anything in Earth. Power must be delivered from distant sunlit areas. Heat must be carefully controlled to avoid losing the very ice being harvested. Even if this can be done, the scale is limited. The total amount of water ice on the moon is uncertain, but estimates suggest it is far less than what would be needed to support large populations. It is a resource for experiments, not salvation. More importantly, the presence of ice does nothing to solve the moon's fundamental problems. Ice does not create an atmosphere. Ice does not generate gravity. Ice does not produce a magnetic field. Ice does not protect against radiation. You can mine ice, but you cannot mine habitability. This is where comparisons to Antarctica often mislead. People imagine the moon's poles as harsh but manageable, like a frozen desert on Earth. The analogy fails. Antarctica still has air, still has pressure, still has protection from radiation, still has gravity strong enough to keep water liquid when heated, still has a global ecosystem and atmospheric circulation. The moon has none of this. If Antarctica is a hostile outpost on a living planet, the moon's poles are sealed vaults in a dead world. Another misconception is that the moon's water suggests it once had oceans. There is no evidence for this. The distribution of water is patchy and localized. It does not form layers or deposits consistent with ancient seas. It does not appear in equatorial regions where oceans would have existed. It exists precisely where physics allows it to hide. This reinforces the conclusion that the moon was dry early on and remained so. Water did not shape the moon. It merely survived in a few protected corners, and survival is not the same as habitability. This brings us to a deeper misunderstanding about what makes a world alive. Life does not need water alone. It needs cycles. It needs movement. It needs energy gradients that persist without destroying complexity. It needs time spent in stable conditions. The moon offers none of this on its surface. Energy arrives violently during the day and vanishes at night. Radiation destroys complex molecules. Temperature swings shatter materials. Gravity allows everything to escape. The environment does not nurture, it erodes. Ice trapped in shadow is not a beginning. It is an ending, a reminder that even essential ingredients become static when the environment cannot support change. This is why the moon, despite its proximity and familiarity, remains fundamentally unsuitable for anything resembling a natural ecosystem. It can host machines. It can host temporary human presence. It can serve as a laboratory or a stepping stone, but it cannot become alive. Understanding this helps correct another dangerous illusion: the idea that we can terraform the moon. If water exists, people ask, why not add more? If there is ice, why not melt it? If the moon is close, why not fix it? In the next part, we will confront this idea directly. Terraforming, not as science fiction, but as an engineering and physical problem. We will ask what it would actually take to turn the moon into something resembling Earth, and why the answer is far more brutal than most imagine when terraforming the moon. An engineering fantasy meets physics. Once water is mentioned, the idea of transformation quickly follows. If the moon has ice, why not melt it? If it lacks air, why not? If it is cold at night, why not regulate temperature? Terraforming sounds like a problem of scale, not of principle. Given enough technology, enough energy, enough time, anything should be possible. This belief collapses the moment physics is taken seriously. Terraforming is not the act of improving a world. It is the act of fighting everything that makes that world what it is. On the moon, this fight be endless, energy-intensive, and ultimately unwinnable. Let us begin with the most obvious requirement: an atmosphere. To make the moon even marginally Earth, it would need an atmosphere thick enough to provide pressure, regulate temperature, and shield the surface from radiation. A minimal target might be 1/10 of Earth's atmospheric pressure. Anything less than liquid water remains unstable. Where would atmosphere come from? One proposal is to release gases from lunar materials. Heating the regolith could release trapped oxygen. Ice could be vaporized into water vapor. Imported volatiles from comets or asteroids could be added. Even if all of this were done, the numbers are unforgiving. To create an atmosphere with 1/10 of Earth's pressure, the moon would need roughly 10 trillion tons of gas. That is not a rounding error. That is a mass comparable to large asteroids. Transporting it would require moving objects tens of kilometers wide across the solar system. Releasing it would require energy on a planetary scale. But even if this impossible feat were achieved, the atmosphere would not stay. The moon's gravity is too weak. Gas molecules would escape continuously. The lighter the gas, the faster the loss. Hydrogen would vanish almost instantly. Water vapor would break apart under ultraviolet radiation. Oxygen and nitrogen would leak away over thousands to millions of years. On human timescales, this might seem acceptable. But terraforming is not about years. It is about permanence. Any atmosphere created on the moon would be temporary. It would require constant replenishment. Terraforming would not be a one-time project. It would be a forever expense. Next, temperature. Without an atmosphere, the moon experiences extreme temperature swings. With an atmosphere, those swings would be reduced, but only if the atmosphere were thick enough. A thin atmosphere would still fail to redistribute heat effectively. To maintain stable temperatures, greenhouse gases would be required. But greenhouse gases trap heat by absorbing infrared radiation. On the moon, trapped heat would still radiate into space quickly because the planet itself has little thermal inertia. Earth moderates temperature because it has oceans, thick crust, and active geology. Heat is absorbed, stored, and redistributed. The moon has none of these systems at scale. Even with an artificial atmosphere, nights would remain brutally cold. Days would remain intensely hot. Weather systems would be weak or non-existent. Climate would be unstable. Then, there is radiation. An atmosphere alone does not protect against all radiation. Earth's protection comes from a combination of atmosphere and magnetic field. Without a magnetic field, charged particles from the solar wind penetrate deep into the upper atmosphere, stripping it away and irradiating the surface. To truly terraform the moon, one would need to create an artificial magnetic field. This is where proposals become almost surreal. One idea involves placing a massive magnetic generator at the Moon-Earth L1 point, creating a magnetic shield that envelops the moon. Another suggests building a network of superconducting rings around the moon's equator. These ideas require energy outputs rivaling those of entire civilizations. They also require materials maintenance and stability beyond anything humanity has ever attempted. And even if such a field were created, it would still not solve the gravity problem. Magnetism can deflect particles. It cannot stop molecules from drifting away under thermal motion. The moon would still leak atmosphere. The field would slow erosion, not prevent it. Then, water. Suppose ice is melted. Suppose more water is delivered. Suppose liquid water flows briefly on the surface. What happens next? At lunar pressure, water boils. To prevent this, pressure must be maintained. That brings us back to atmosphere. Without constant replenishment, pressure drops, water evaporates, ultraviolet radiation breaks it apart. Hydrogen escapes. Oxygen reacts with rocks or escapes. The moon does not recycle water. There is no hydrological cycle, no clouds, no rain, no rivers returning water to reservoirs. Water on the moon would be a one-way resource moving steadily toward loss. Terraforming Earth works because Earth already does most of the work itself. Terraforming the moon would mean everything manually, forever. Now consider timescales. Terraforming is often imagined as a project lasting centuries, perhaps 1,000 years. But planetary processes operate on millions and billions of years. Any system imposed on the moon would be constantly fighting natural processes that never stop. If maintenance failed for even a relatively short time, the moon would revert. Atmosphere would thin. Water would vanish. Radiation would return. The system would collapse. This makes lunar terraforming fundamentally different from any engineering project on Earth. It is not building a city. It is not even building a planet. It is holding a planet in a state it does not want to be in. There is also a deeper issue that rarely gets discussed. Energy. Every step of terraforming requires energy to move mass, to heat materials, to generate magnetic fields, to replenish lost gases, to repair damage from radiation and micrometeorites. Where does this energy come from? Solar power is limited by day-night cycles and low solar angles. Nuclear power introduces waste and risk. Fusion remains theoretical. Importing energy from Earth defeats the purpose. A terraformed moon would not be self-sustaining. It would be dependent, permanently. At this point, the idea stops being about creating a new world and starts being about maintaining a fragile artificial environment in an openly hostile setting. And this leads to a crucial realization. Terraforming the moon is not about making the moon habitable. It is about exporting Earth's life support systems into space and spreading them thin. Every resource spent trying to fix the moon is a resource not spent protecting Earth. Every technology designed to hold air on the moon could be used to prevent atmospheric collapse on our own planet. Every joule spent fighting lunar physics could be spent stabilizing terrestrial systems that already support life naturally. This does not mean the moon has no value. It has immense value as a scientific archive, as a testing ground, as a place to learn how humans survive in extreme environments, as a stepping stone for deeper space missions. But it is not a second Earth, never will be. The moon is what it is because physics made it that way. No amount of ambition can rewrite its mass, its gravity, its history, or its relationship with the sun. Terraforming fails not because we lack imagination, but because imagination does not change escape velocity. In the next part, we will move below the surface. If the moon is uninhabitable above ground, could it be livable beneath it? Lava tubes, underground caverns, and the idea of hiding from space rather than conquering it below the surface. Hiding from space instead of conquering it. When the surface of a world is too hostile to inhabit, the natural response is to go underground. This instinct is as old as life itself. On Earth, organisms retreated beneath the surface to escape radiation, temperature extremes, and environmental chaos long before complex life appeared above ground. Faced with the moon's brutal surface conditions, scientists and engineers have arrived at the same conclusion. If humans are ever to live on the moon for extended periods, it will not be on the surface. It will be beneath it. The moon is not a solid block of rock. Beneath its cratered surface lies a hidden network of vast underground structures formed billions of years ago when the moon was volcanically active. These structures are known as lava tubes. Lava tubes form when molten rock flows across the surface, and the outer layer cools and hardens while the interior continues to flow. When the lava dries, it leaves behind long, hollow tunnels. On Earth, lava tubes can be tens of meters wide and kilometers long. On the moon, they be far larger. Because lunar gravity is low, lava flows behave differently. The roof of a lunar lava tube could span hundreds of meters without collapsing. Some estimates suggest lunar lava tubes could be wide enough to contain entire cities. This discovery transformed how scientists think about lunar habitation. Inside a lava tube, many of the moon's most dangerous problems disappear or become manageable. Radiation is the first to go. A few meters of rock are enough to block nearly all cosmic radiation and solar particles. Inside a lava tube, radiation levels could be comparable to those on Earth's surface. This alone makes underground habitats vastly safer than anything built on the surface. Temperature is next. Below the surface, temperature remains remarkably stable. While the lunar surface swings between extreme heat and cold, underground temperatures change slowly and stay within a narrow range. This stability is essential for long-term human presence and for maintaining equipment, life support systems, and stored resources. Micrometeorites also vanish as a threat. The moon is constantly bombarded by tiny impacts because it lacks an atmosphere. On the surface, this erosion never stops. Underground, it becomes irrelevant. Lava tubes have survived intact for billions of years, suggesting they are structurally stable on geological timescales. In this sense, the moon's greatest weakness becomes an advantage. The very processes that stripped it of atmosphere and life preserved an untouched underground environment. A natural bunker against space itself. This leads to a subtle but important shift in thinking. We stop asking how to make the moon Earth-like and start asking how to adapt humans to the moon. This is a far more realistic approach. An underground lunar habitat would not require terraforming. It would not require a global atmosphere. It would not require a magnetic field. It would rely on localized life support, shielding, and controlled environments, much like submarines or space stations, but with the added benefit of natural protection. However, this approach comes with its own limitations. An underground habitat is not a living world. It is an enclosed system. Every breath, every drop of water, every nutrient must be recycled. Any failure in life support be critical. The margin for error is small. Such habitats would resemble isolated research stations rather than cities. Sustainable for small population, unsuitable for millions. Psychological challenges also emerge. Living without open skies, without natural day-night cycles, without weather, wind, or open landscapes, humans evolved under sunlight and wide horizons. Extended confinement underground affects mental health, social dynamics, and long-term well-being. Even if technology solves physical survival, it cannot easily solve psychological strain. There is also the question of resources. Lava tubes provide shelter, not sustenance. Food must be grown artificially. Water must be imported or mined from polar ice and transported. Energy must be generated reliably. Waste must be managed perfectly. Nothing about this system is self-sustaining, and this reveals an important truth. Living underground on the moon is not a step toward planetary colonization. It is a step toward learning how to survive environments that will never support us naturally. In other words, it is training. Training for deep space missions. Training for Mars. Training for long-duration isolation. Training for managing closed ecosystems under extreme constraints. The moon becomes a classroom, not a destination. This perspective aligns with reality far better than dreams of lunar cities under domes. Domes on the surface are fragile. One impact, one failure, and everything is lost. Underground habitats offer resilience, but at the cost of scale and freedom. The moon, even at its most accommodating, remains a place humans can visit, study, and temporarily inhabit. It is not a place where humanity can spread freely or build a parallel civilization. And this returns us to the deeper theme running through every part of this story. Not every world meant to be lived on. Some worlds exist to be understood. The moon is one of them. In the next part, we will confront a question that naturally follows. If even underground living on the moon is limited, what does this tell us about humanity's future beyond Earth? Are other nearby worlds any more forgiving? Or does the moon represent a universal lesson about planetary limits, the final illusion? Why space will never become a second home? At this point, the pattern should be impossible to ignore. Every time humanity looks outward and imagines a future among the stars, reality pushes back. Not gently, not gradually, with absolute indifference. The moon cannot sustain life on its surface. Mars is colder, thinner, and more hostile than we once believed. Venus is a furnace. Mercury is an oven and a freezer stitched together. The outer moons hide oceans beneath kilometers of ice, sealed away from sunlight and open skies. Exoplanets that look promising from afar reveal lethal radiation, unstable stars, or impossible distances. Again and again, the same conclusion emerges. Space does not want us. This is not pessimism. It is physics. The universe is not structured for biological comfort. It is structured by gravity, radiation, entropy, and time. Life is not the rule. Life is the exception, and intelligent life is a rare exception layered on top of another. Earth did not become habitable because the universe favors life. Earth became habitable because an extraordinary number of conditions aligned at once and remained aligned for billions of years. A stable star, a protective magnetic field, a thick atmosphere, liquid water on the surface, plate tectonics regulating climate, a large moon stabilizing axial tilt, a location away from frequent supernovae, enough gravity to hold gases but not crush biology. Remove any one of these, and the experiment fails. The moon shows us what happens when most of these conditions are missing. It is not broken. It is not unfinished. It is exactly what a world looks like when life never truly gains a foothold. This realization forces us to confront a difficult truth about the future of humanity. We are not pioneers standing at the edge of an open frontier. We are custodians standing inside a narrow refuge. For centuries, human expansion followed the same pattern. There was always somewhere else to go. Another continent, another ocean, another horizon. Every limit turned out to be temporary. Space feels like the next step in that story, but it is not. Space, not an extension of Earth. It is a different regime entirely. On Earth, mistakes are survivable. In space, mistakes are fatal. On Earth, ecosystems repair themselves. In space, nothing heals without constant intervention. On Earth, life spreads naturally. In space, life must be carried, shielded, and maintained against relentless decay. This is why large-scale space colonization remains an illusion. Not because we lack ambition, not because we lack intelligence, but because the environment itself is fundamentally incompatible with biological life. We can build stations, we can build underground bases, we can send probes and robots farther than ever before. But every step away from Earth increases fragility instead of reducing it. The farther we go, the more artificial our existence becomes, and artificial systems always fail eventually. This does not mean exploration is meaningless. On the contrary, it means exploration must be understood for what it truly is. Not an escape plan, not a backup civilization, not a path to immortality, but a way to understand our place. The moon teaches us restraint. It teaches us that proximity does not equal accessibility, that similarity does not equal safety, that resources do not equal habitability. It teaches us that survival is not guaranteed by technology alone. This lesson extends far beyond the moon. If red dwarfs dominate the galaxy and most of them are hostile, then habitable worlds are rarer than we hoped. If interstellar travel is limited by distance and energy, then civilizations are isolated by nature. If cosmic catastrophes can erase progress without warning, then permanence is an illusion everywhere. This reframes the famous question, where is everybody? The answer would be unsettlingly simple. They are trapped by distance, confined by physics, vulnerable to chance. Civilizations may rise, think wonder, and disappear without ever touching another star. Not because they failed, but because the universe not permit otherwise. And this leads to the most important conclusion of all. Earth is just our home. It is our realistic home, not for centuries, not for millennia, but for the foreseeable future measured in the language of physics. This does not diminish humanity. It elevates responsibility. Every forest destroyed, every ocean polluted, every climate destabilized. There is no replacement waiting among the stars. The moon will never become Earth. Mars will never forgive us. The stars will never welcome us. But Earth already has. Against overwhelming odds, it allowed life to flourish. Against comic violence, it protected complexity. Against entropy, it sustained meaning, and ended so quietly, without promise of rescue, without guarantee of permanence. Just enough time. The universe is vast, cold, and indifferent, yet we are thinking, questioning, understanding. That may be the phenomenon of all. And if there is a future worth protecting, it is not scattered across the galaxy. It is right beneath our feet, last perspective. Why knowing our limits may save us. When people hear that space will never become a second home, the reaction is often emotional, disappointment, resistance, even anger. The idea clashes with decades of stories, dreams, and cultural momentum that painted the cosmos as humanity's destiny. But truth does not exist to comfort us. Truth exists to orient us, and orientation matters. Because misunderstanding our place in the universe is far more dangerous than accepting its limits. For a long time, humanity believed the Earth was the center of everything. Then we learned it was not. Later, we believed the sun was special. Then we learned it was one star among hundreds of billions. Each time, perspective widened, and each time, the truth felt smaller and colder than the stories that came before. Now, we faced its correction. The universe is not a waiting room for civilizations. It is not a ladder of progress. It is not a stage designed for expansion. It is a vast physical system that allows complexity to exist only in narrow, fragile pockets. Earth, one of those pockets. Understanding this does not trap us. It frees us from dangerous fantasies, because fantasies lead to neglect. If people believe there is another Earth waiting somewhere, they tolerate damage here. If they believe humanity will escape to Mars or beyond, they accept collapse as temporary. If they believe technology will save us regardless of physics, they stop respecting constraints. This is not hypothetical. History shows the pattern clearly. Every time a civilization believes it has unlimited expansion ahead, it overshoots. It consumes faster. It preserves less. It postpones responsibility. The idea of space as a backup world has quietly encouraged this mindset, but there's no backup. not in any time frame that matters. Once this sinks in, priorities shift. Space exploration becomes about knowledge, not salvation. Telescopes become mirrors for understanding rather than scouting tools for escape. Probes become witnesses, not pioneers. Science becomes humility rather than conquest. This reframing also changes how we think about intelligence in the universe. If other civilizations exist, they are likely bound by the same walls. They may look at their skies with the same mixture of wonder and frustration. They may build telescopes instead of starships. They may map exoplanets they will never reach. They may debate the same illusions, and they may conclude the same thing: that survival is local, that meaning planetary. That progress is measured not by distance traveled, but by stability achieved. This would explain the silence, not as absence, but as confinement, not as failure, but as equilibrium. Civilizations that survive long enough to understand reality may choose caution over expansion. They may reduce emissions instead of building armadas. They may protect oceans instead of chasing stars. They may invest in longevity rather than reach. Silence may be the sound of wisdom. There is another uncomfortable implication. If civilizations that ignore limits tend to destroy themselves, then the true great filter may not be behind us. It may be ahead, not in the form of alien threats or cosmic disasters, but in the form of self-inflicted collapse driven by denial. Climate instability, ecological collapse, resource exhaustion, technological fragility. These are not separate problems. They are symptoms of one mistake: believing we live in an infinite universe when we inhabit a finite refuge. The moon teaches this lesson brutally: close enough to reach, familiar enough to feel safe, dead enough to reveal the truth. It shows what happens when protection is lost, when atmosphere escapes, when magnetism fades, when water vanishes, when time erodes everything without resistance. It is Earth without mercy. And that, the moon matters. Not as a destination, but as a warning. A reminder in stone. From orbit, Earth and the moon are together. One blue, one gray, one alive, one silent. They formed from the same event. They share a history, yet their paths diverged completely. The difference, chance alone. It is protection. Protection, everything. Protection from radiation. Protection from vacuum. Protection from chaos. Earth is a shielded oasis in a hostile sea. And oases do not forgive carelessness. This leads to the final, unavoidable conclusion. The most important space project humanity can undertake is not on the moon, Mars, or beyond. It is here. Maintaining a stable climate, preserving biodiversity, protecting oceans, sustaining soil, preventing runaway technological risks. These are not environmental issues. They are survival issues on a cosmic scale. Because if Earth fails, nothing replaces it. Not Proxima b, not Mars, not underground habitats, not generation ships drifting between stars. Silence. The irony, profound. We search the universe for signs of life, while slowly damaging the only confirmed living world we know. We dream of distant skies, while polluting our own. We fear cosmic extinction events, while engineering one locally. Yet, standing our limits offers hope. Not false hope, not escapist hope, but grounded hope. Hope on responsibility. Hope based on awareness. Hope based on choosing endurance over expansion. If humanity accepts that it is not destined to spread across the galaxy, it may finally learn how to stay, to stabilize, to adapt, to mature. And that may be the rarest transition of all. Not from planet to planet, but from adolescence to wisdom. The universe does not promise us eternity. It offers some moment, a fragile window in which consciousness can exist and reflect on itself. The moon reflects sunlight. Earth reflects meaning. One shows us what is left when life never takes hold. The other shows us what is possible when it does. That contrast is not tragic. It is clarifying. And clarity may be the greatest gift the cosmos has given us, the quiet ending. What remains when the universe does not answer? At the very end of this journey, there is no dramatic revelation waiting. no hidden shortcut through physics, no sudden technological miracle that changes everything. There is only clarity, and clarity is then hope. When humanity first began to look at the stars, we projected ourselves onto them. We imagined destinations, futures, descendants living under alien suns. We turned the universe into a stage for our ambition. That was understandable. Every intelligent species begins by assuming it is the story. But maturity begins when a species learns it is a paragraph, not a book. The universe does not respond to intention. It does not reward curiosity with permission. It does not bend for dreams. It operates according to rules that existed long before thought and will continue long after memory fades. Distance does not care that we want to cross it. Radiation does not pause for civilization. Entropy does not negotiate. And yet, within these constraints, something extraordinary happened. On one small planet, in one quiet system, matter organized itself enough to ask questions. That is not destiny. That is not entitlement. That is an accident of breathtaking rarity. The moon orbits Earth as a reminder of what most worlds become: silent, stripped, frozen in time. It is not hostile. It is indifferent, the same indifference that governs the rest of the cosmos. The tragedy is not that the universe is dangerous. The tragedy would be failing to understand that it is, because once we understand this, the narrative changes. We stop treating Earth as a launch pad. We stop treating space as an escape. We stop measuring success by expansion alone. We begin to measure it by continuity. Can we persist without destroying the conditions that allow us to exist? Can we advance without destabilizing the systems that protect us? Can we grow wiser instead of merely more powerful? These questions matter more than propulsion systems or colony plans. Technology increases reach. Wisdom increases survival. The universe filters relentlessly, not through intention, but through consequence. Anything that grows without balance collapses. Anything that ignores limits breaks. Anything that assumes permanence invites correction. Stars explode, planets sterilize, civilizations vanish, not because they are punished, because physics is patient. From a cosmic perspective, intelligence is a brief flare. It appears, reflects, and often disappears before leaving a trace. The galaxy may be filled with ruins we will never see, stories that never crossed the void, not because they were alone, but because they were separated by silence enforced by reality. If there are others out there, they may be doing exactly what we are doing now. Looking, learning restraint, choosing survival over spectacle, or they may already be gone. We will know. And that uncertainty is not a flaw in the universe. It is a mirror. The final illusion is believing that meaning requires an audience. It does not. Meaning exists because consciousness exists, because awareness happened at least once, because for a moment, the universe became capable of noticing itself. That moment is now. Earth. With us, not later, not elsewhere, here. The stars will continue to burn long after humanity is gone. Proxima Centauri will flare for trillions of years. Black holes will drift. Galaxies will collide. Eventually, even stars will fade. None of this needs witnesses. But right now, there is one. A fragile species standing on a thin layer of rock and air, aware of its limits, aware of its danger, aware of its responsibility. This awareness is not weakness. It is strength, refined by truth. We may never cross the stars. We may never touch another living world. We may never escape the boundaries written into space and time. But within those boundaries, we can choose how we exist. Whether we burn fast or endure. Whether we conquer or preserve. Whether we deny reality or live in harmony with it. The universe does not care which choice we make. But we do. And that is enough. This is not a story about despair. It is a story about precision, about knowing exactly where we stand, between infinite darkness and a single fragile light. As long as that light remains, the universe is not entirely silent. And that quiet ending, not with escape, but with understanding, after the silence, what humanity does with there is nowhere else to go. After everything that has been said, After every illusion stripped away, a strange question remains, not about space, not about stars, but about us. What does a civilization do when it finally understands that escape is not coming? For most of human history, pressure was relieved by movement. When land was exhausted, people migrated. When resources declined, borders expanded. When systems failed, new frontiers absorbed the consequences. Expansion acted as a release valve. Space removed that illusion, because space offers no release. Once this truth settles in, humanity enters a new phase. A phase no civilization before us has clearly reached. A phase where survival depends not on reaching outward, but on stabilizing inward. This is a profound evolutionary shift. Biological evolution rewards spread. Cultural evolution often rewards dominance. But planetary survival rewards. The instincts that once carried us across continents now threaten us on a finite world. The moon, Mars, and the stars expose this contradiction mercilessly. They do not care about ambition. They respond only to physics. So what remains is adaptation of a different kind. Not adaptation to space, adaptation to limits. This is the most difficult adaptation any intelligent species can face, because feel like failure. For thousands of years, progress meant more land, more power, more speed, more energy, more growth. But infinite growth in finite boundaries is not progress, it is collision delayed. A civilization that understands this must rewrite its definition of success. Success becomes resilience instead of dominance, efficiency instead of excess, longevity instead of acceleration. This does not mean stagnation, it means refinement. The future of humanity, if it exists, will not look like star empires or galactic migrations. It will look quieter, more precise, less dramatic. Cities optimized rather than expanded. Energy systems closed rather than extractive. Technologies designed to endure rather than impress. This kind of future does not inspire movies, but it inspires survival. There is a reason this idea feels uncomfortable. It contradicts our myths. From the earliest stories, heroes leave home. They cross seas. They conquer unknown lands. They bring back power, knowledge, transformation. Staying has rarely been glorified, but the cosmic era forces a reversal. Leaving is easy in stories. Staying is hard in reality. Staying means repairing instead of abandoning. Staying means restraint instead of conquest. Staying means responsibility without applause. If there is a great filter ahead, it is likely here. Not in space, not in alien contact, not in cosmic disasters, but in whether intelligence can coexist with its own power. Technology amplifies consequences faster than wisdom evolves. That gap is dangerous. Nuclear weapons, climate systems, artificial intelligence, biological engineering. These are not separate threats, they are expressions of the same imbalance. Power without restraint. The universe does not correct this for us. It allows civilizations to fail quietly. The silence of space may be filled with lessons written in absence. Worlds where intelligence burned itself out. Worlds where technology outpaced wisdom. Worlds that never learned to stop. If such civilizations existed, their ruins are likely invisible. Their signals too brief. Their expansions too fragile. We should not assume we are different by default. Difference must be earned. This brings us to a final reframing of hope. Hope is not that humanity will conquer space. Hope is that humanity will learn to remain humane under pressure. Hope is not immortality. Hope is continuity long enough for meaning to accumulate. Hope is not escape. Hope is stewardship. Earth is just a planet. It is a test of whether intelligence can stabilize itself. A test of whether awareness can override instinct. A test of whether foresight can guide power. Passing this test guarantees eternity. Nothing does. But failing it guarantees extinction. The universe will continue either way. Stars will burn, galaxies will turn, time will pass. The question is whether consciousness remains part of that process. And consciousness, unlike stars, requires care. It requires systems that do not collapse. Cultures that value truth over comfort. Decisions made for centuries instead of quarters. This is not a call for despair. It is a call for maturity. The moon does not mock us, it instructs us. It shows us what happens when protection is lost. It shows us how fragile habitability is. It shows us that dead worlds are the default state, Earth, the anomaly. And anomalies must be protected, not exploited. If there is a future chapter to this story, it will not be written among the stars. It will be written quietly, in forests preserved, in oceans restored, in cities redesigned, in technologies restrained. It will be written by a species that finally understands that the most advanced act is not expansion. It is care. Because in a universe that offers no mercy, choosing to protect life is the most radical decision imaginable, a long view. What survives when everything else fades? At some point, every intelligent species must confront a question that has no technical solution. Not a problem to be engineered away. Not a barrier to be broken by innovation. A question that exists beyond tools and equations. What is worth preserving when nothing lasts forever? The universe teaches impermanence at every scale. Stars burn out. Planets erode. Galaxies drift apart. Even atoms are not eternal. Time is not a background. It is an active force, quietly dismantling everything that exists. Against this backdrop, intelligence is not powerful. It is temporary. And yet, temporariness does not make something meaningless. It makes it precious. For a long time, humanity measured success by how much it could build, how far it could reach, how fast it could grow. But growth is not the same as endurance. In fact, unchecked growth is often the opposite. The civilizations that last longest are rarely the loudest. They are the ones that learn when to stop. This is the final lesson hidden inside the moon, inside Proxima Centauri, inside every hostile world we have examined. The universe does not reward ambition. It rewards alignment with reality. A star does not care if you want to orbit it. A vacuum does not care if you need air. Radiation does not care if life depends on stability. The cosmos offers conditions. It does not negotiate outcomes. Earth happened to fall into a narrow window where complexity could persist. That window is not guaranteed to stay open. It requires active maintenance, not passive hope. This is where the future of humanity truly resides. Not in rockets, not in colonies, not in distant suns, but governance of ourselves. Can we slow down when acceleration feels natural? Can we reduce consumption without collapse? Can we design systems that assume failure and recover gracefully? Can we think in centuries instead of election cycles? These are not political questions. They are survival mechanics. A civilization that cannot regulate itself will always be destroyed by its own capabilities long before the universe needs to intervene. In this sense, space exploration has already done its job. It has the truth. It has stripped away fantasy. It has removed false exits. It has revealed that there is no cosmic safety net, and now the responsibility returns home. There is something deeply unsettling about realizing that the universe does not need us, does not watch us, does not judge us. There is external validation. No applause. No destiny written in the stars. Meaning must be created locally or not at all. But this is liberating. If meaning is not assigned by the universe, then it is chosen. Chosen by how we treat each other. Chosen by how we treat the biosphere that sustains us. Chosen by whether we value understanding over domination. In a universe of indifference, care becomes an act of rebellion. This reframes of legacy. Legacy is not monuments that outlast stars. Legacy is not artifacts drifting between galaxies. Legacy is continuity. The continuation of thought, the continuation of culture, the continuation of memory. As long as intelligence exists somewhere, even briefly, the universe is not entirely unconscious, and may be enough. One day, far in the future, Earth will no longer be habitable. The Sunday will brighten, rose will boil, life will retreat and vanish. This is inevitable. Physics guarantees it, but inevitability does not erase responsibility in the present. A candle will burn out. That does not mean it should be knocked over. We're living in the bright interval, the rare chapter where the universe allows awareness to exist. What we do with this interval matters, not because it will echo forever, but because it exists at all. The stars will never be homes. The moon will never forgive us. The universe will never adapt to our needs, but Earth already has. And Earth does not need to be conquered. It needs to be understood, maintained, protected. This understanding is not small. It is not defeat. It is not surrender. It is alignment with truth. And truth, even when cold, is the only solid foundation anything has ever stood on. If there is wisdom in the cosmos, it is not spoken. It is implied, by silence, by distance, by fragility. The universe tells us, without words, that survival is not guaranteed, expansion is not promised, and meaning is not given. Meaning, chosen. Right now, here, on this world. And that choice is the final frontier humanity will ever face, the final choice. What kind of species we decide to be. After everything that has been stripped away, there is only one question left. Not a scientific one, not a cosmic one, a moral one. What kind of species are we going to be? Not what we can build, not how far we can reach, not how powerful we can become, but how we behave, understand the truth. Because understanding changes responsibility. Before telescopes, ignorance was natural. Before satellites, climate was abstract. Before space probes, the universe was myth. But now we see clearly. We see how rare habitable worlds are. We see how fragile Earth is. We see how hostile everything else truly is. We can no longer pretend. There is no second cradle. There is no hidden refuge. There is no cosmic reset button. This planet is not practice. It is the only exam. And exams are not passed by ambition alone. They are passed by discipline. The most dangerous moment in the life of a civilization is not when it is weak, but when it becomes powerful without wisdom. When it can alter climate but not agree on restraint. When it can destroy itself faster than it can protect itself. When it mistakes capability for destiny. Power expands faster than maturity. That imbalance has ended civilizations before. On smaller scales, on single continent, on single worlds, if the universe is honest about its silence. The moon stands as a fossil of failure not because something went wrong, but because nothing went right enough. No atmosphere retained. No magnetic shield maintained. No long-term stability preserved. Earth succeeded where the moon failed, not because it was destined to, but because conditions aligned. Now those conditions depend on us. This is unprecedented. For the first time, a planet's future is shaped by a species that understands what it is doing. For the first time, extinction is no longer only an accident. It is a choice delayed. That is a terrifying level of agency. And yet, it is also extraordinary, because it means we are no longer children in the universe. Children break things without understanding the consequences. Adults know that some damage cannot be undone. The illusion of cosmic expansion allowed us to postpone in adulthood. To imagine that mistakes could be escaped. That failure here could be replaced elsewhere. That illusion is over. Now the future becomes quieter, more careful, more deliberate, not smaller, deeper. Progress will no longer be measured by distance traveled, by damage avoided. Not by energy consumed, but by stability preserved, not by dominance achieved, but by systems sustained. This kind of progress does not produce empires, it produces continuity. Continuity is rare. Continuity requires restraint. Continuity requires cooperation. Continuity requires long memory. Civilizations that survive long enough to understand limits may become nearly invisible from the outside. Low emissions, controlled energy use, minimal cosmic signatures, few signals, little waste. From afar, they might look like silence. And this reframes the final mystery. Maybe the universe is not empty. Maybe it is quiet because those learn to whisper. If that is true, then the silence we hear is not a warning of doom. It is an invitation to maturity, an invitation to stop shouting into the void and start listening to the world beneath our feet. The stars are not calling us to them. They are reminding us how rare home is. The moon is not waiting to be claimed. It is waiting to be understood. Space, an escape route. It is a mirror, and what it reflects is simple and unforgiving. We are alone in responsibility. even if we are not alone in existence. There is no cosmic parent, no galactic referee, no rescue fleet, only consequences and choice. This is where the story truly ends. Not with a launch, not with a discovery, not with a message from the stars, but with a decision made quietly, collectively, and continuously to protect the only known island of life, to accept limits without despair, to value wisdom over reach. If humanity fails, the universe will not notice. But if humanity succeeds, even briefly, the universe will have done something remarkable. It will become aware of itself, and that awareness, however temporary, is not meaningless. It is everything what comes after understanding, living with the truth instead of escaping it. Once the final choice is recognized, something subtle but irreversible happens. The universe does not change, the stars do not soften, the distances do not shrink. We do. Understanding alters the way a civilization breathes. For a long time, humanity lived as if the future were guaranteed, as if tomorrow was automatic, as if continuity required no effort. That illusion was comfortable. It allowed excess. It allowed delay. It allowed the belief that consequences belonged to someone else, somewhere else, someone else. Cosmic reality removes that comfort completely. There is no somewhere else. There is only now, stretched thin across generations. Living with this truth is not dramatic. It does not look like revolution. It does not arrive with speeches or flags. It arrives quietly, through changed priorities and abandoned fantasies. A mature civilization does not ask how far it can go. It asks how long it can last. This shift is invisible from the outside, but profound from within. Science becomes less about conquest and more about preservation. Energy becomes something to manage, not something to extract endlessly. Technology becomes a tool for resilience, not acceleration. Growth becomes qualitative rather than quantitative. The most important breakthroughs will not be louder engines or taller structures. They will be systems that fail safely, cultures that adapt without breaking, economies that stabilize instead of expand forever. These are not limits imposed by fear. They are limits chosen by understanding. This is where many people misunderstand restraint. They confuse it with surrender. It is not. Restraint is the highest form of control. A species that can choose not to exploit everything it can reach is no longer governed by impulse. It has crossed a threshold most life never approaches. Impulse spreads, wisdom endures. From this perspective, the moon, Mars, and the stars still matter. But they matter differently. They become teachers. The moon teaches fragility. Mars teaches loss. Red dwarf systems teach hostility. Deep space teaches indifference. Each lesson removes another layer of fantasy and replaces it with clarity. And clarity is the of responsibility. The next centuries, if they exist, will not be defined by expansion into space. They will be defined by stabilization on Earth. By learning how to live within planetary boundaries without collapsing under political, cultural, or technological stress. This will be slow, uneven, imperfect. But perfection was never required, only persistence. One of the hardest truths to accept is that meaning does not increase with scale. A galaxy-wide civilization is not more meaningful than a planetary one. Awareness does not become deeper because it spreads farther. Consciousness does not become richer by occupying more volume. Meaning comes from continuity and depth, not distance. A single planet sustaining thought for millions of years contains more significance than 1,000 colonies that burn out in centuries. The universe does not reward speed. It rewards alignment. This understanding also dissolves one final illusion. The idea that humanity must leave a permanent mark on the cosmos to matter. Not. Most stars leave no memory. Most galaxies will fade beyond observation. Even atoms forget their origins. Impermanence is not failure. It is the default state of reality. What matters is not that something lasts forever, but that it existed at all. That thought occurred. That beauty was perceived. That understanding emerged from chaos. These are not by time. They happened, and is enough. So what does living with the truth look like on an ordinary day? It looks like protecting systems we did not create but depend on. It looks like designing technology that assumes future humanity. It looks like choosing cooperation when competition threatens collapse. It looks unspectacular, and that may be its greatest strength. Civilizations that chase spectacle burn bright and fast. Civilizations that choose care burn quietly and long. The universe is full of burned-out lights. Earth. That light does not come from ambition. It comes from balance. If humanity ever reaches the point where it truly understands this, then space will have fulfilled its role without ever being colonized. It will have taught us who we are. Not conquerors of the void, not children of destiny, but caretakers of a rare moment. A moment where matter learned to think. A moment where silence learned to ask questions. A moment where the universe looked inward and recognized itself. That moment does not need to spread across stars to be meaningful. It only needs to last a last horizon. Why staying is the hardest journey of all. There is a temptation, even after everything we now understand, to believe that meaning still lies somewhere ahead, somewhere beyond the next breakthrough, the next discovery, the next horizon. This instinct is deeply human. It carried us out of caves, across oceans, and into orbit. But the instinct that once ensured survival now confronts a universe that does not open further doors. The final horizon is not in space. It is internal, staying harder than leaving. Leaving allows fantasy. Staying demands accountability. When a civilization accepts that it cannot outrun its consequences, every decision gains weight. Every generation inherits not only knowledge, but responsibility. The future stops being abstract and becomes personal. This is the moment where intelligence either matures or collapses. To stay means to accept limits without resentment. To stay means to repair instead of abandon. To stay means to live with the long echo of actions. This kind of endurance has no soundtrack, no cinematic climax, no final victory. It is quiet work performed over centuries by people who will never see the final result. And yet, this is the most difficult form of courage. The universe tests civilizations not by how far they can travel, but by how well they can remain stable under pressure. Most structures fail not because of external attack, but because of internal imbalance. Ecosystems collapse, trust erodes, feedback loops accelerate beyond control. These failures look small at first. A slight rise in temperature, a gradual loss of biodiversity, a slow normalization of risk, until suddenly, they are not small at all. Understanding this shifts how we interpret danger. The greatest threats are not meteors or gamma rays. They are cumulative errors. Choices repeated long enough to become destiny. Warnings ignored because they arrive quietly instead of violently. The moon shows us the end state of neglect. Not destruction, not explosion, just silence. No atmosphere to forgive mistakes. No system to buffer instability. No recovery once thresholds are crossed. Earth still has buffers. For now. The most radical act humanity can take is not to expand, but pause. To ask whether the next step improves resilience or merely accelerates collapse. To value redundancy over efficiency. To design for centuries instead of quarters. This kind of thinking feels unnatural because evolution favored speed and advantage, not foresight. But intelligence allows us to override instinct. Only if we choose to. There is no we will. The universe does not grade effort, it records outcomes. Civilizations that learn restraint may persist quietly for a long time. Civilizations that do not may vanish spectacularly or quietly. From a cosmic distance, the difference is irrelevant, but from within, it is everything. Because to exist with awareness, even briefly, is to participate in something extraordinary. The universe does not need witnesses, but right now, it has one. A species capable of understanding the rules that bind it. Capable of recognizing the rarity of its position. Capable of choosing preservation over spectacle. This choice will never be made once. It must be made continuously, by each generation, in each crisis, against each temptation to believe the rules no longer apply. That is why staying the hardest journey. There is no final destination, no moment of arrival, no completion state, only maintenance. And maintenance, paradoxically, is the highest achievement available to intelligence in a hostile universe. If humanity succeeds, it will not be remembered by the stars, but it will have done something rarer than expansion. It will have lasted. In a universe built to erase complexity, endurance is rebellion. And rebellion does not need an audience. It only needs resolve, the weight of time. Why endurance is rarer than brilliance. As the story stretches further, one truth comes heavier with each step forward. Time is not neutral. It is not a backdrop against which unfold. Time applies pressure. Constantly, quietly, relentlessly. Most things do not fail suddenly. They fail gradually. Stars burn steadily for billions of years, then collapse in moments. Ecosystems weaken long before they collapse. Civilizations rot internally long before they fall externally. What ends them is rarely a single blow. It is accumulated strain. Endurance is not passive. It is active resistance against decay. For a civilization, endurance requires something counterintuitive. It requires the ability to slow itself down, to recognize when acceleration becomes instability, to distinguish between growth that strengthens structure and growth that thins it. Brilliance alone is insufficient. History is filled with brilliant societies that collapsed. Extraordinary engineers, powerful economies, sophisticated cultures. None of them lacked intelligence, they lacked restraint. The universe amplifies this pattern. On a planetary scale, small imbalances become irreversible once thresholds are crossed. Atmospheres escape. Ice sheets melt. Feedback loops lock in new states. Recovery, if it occurs at all, takes geological time. Human timescales are short. Political cycles are shorter. Economic incentives are shorter still. This mismatch is dangerous, because the systems that keep Earth stable operate on timescales that do not align with decision-making driven by immediacy. Climate systems, ocean circulation, biodiversity, soil regeneration. These are slow systems. They do not respond to urgency. They respond to consistency. A species that cannot think slowly cannot survive long. This is the deeper challenge by space. The moon is frozen not just physically, but temporally. Nothing changes there quickly. What was lost stayed lost. What vanished did not return. The moon is a record of what happens when recovery is impossible. Earth still allows recovery, but only within limits. Those limits are not moral. They are physical. No negotiation extends them. No ideology overrides them. No technology erases them entirely. Understanding this forces a shift in values. Speed becomes suspect. Scale becomes dangerous. Efficiency becomes conditional. Redundancy becomes essential. Systems built for endurance are inefficient by design. They waste energy. They maintain backups. They allow slack. They sacrifice peak performance for stability. Nature, everywhere. Ecosystems contain redundancy. Multiple species fill similar roles. Energy pathways overlap. Failure in one component does not cascade instantly. This inefficiency is why ecosystems persist. Civilizations that optimize away redundancy optimize themselves toward collapse. Space shows us the cost of brittleness. In space, there is no margin, no backup atmosphere, no recovery after failure. One mistake is final. That is why spaceflight demands extreme caution. And that is why planetary stewardship must adopt the same mindset. Earth is not forgiving like fiction suggests. It is forgiving only once. After that, it remembers. The challenge ahead is not whether humanity can invent better tools. It is whether humanity can accept constraints without treating them as enemies. Limits are not insults. Limits are information. They describe the shape of survival. A civilization that treats limits as problems to eliminate will destroy the conditions that allow it to exist. A civilization that treats limits as guides can align with reality instead of fighting it. This alignment does not feel triumphant. It feels sober. And sobriety is not weakness. It is clarity without intoxication. The universe does not intoxicate itself with hope. It operates with precision. Life that survives learns to do the same. If there is a path forward, it is narrow and unglamorous. It involves governance that values long-term outcomes over short-term wins. Education that emphasizes systems thinking. Cultures that reward preservation as much as innovation. Technologies that are reversible rather than irreversible. None of this guarantees success, but ignoring guarantees failure. The stars will continue without us. That is not cruelty. It is indifference. The same indifference that allows us to exist at all. Within that indifference, endurance is a choice. Difficult one, a continuous one, a quiet one, and perhaps the rarest choice any intelligent species ever makes, the narrow path. Why intelligence must learn to say enough. At some stage, every intelligent species encounters a moment of internal reckoning, not imposed from outside, not triggered by catastrophe, but arising from accumulated understanding. This moment is defined by a single realization, that not everything possible is survivable. For most of evolutionary history, possibility equaled advantage. If something could be exploited, it was. If a resource could be consumed, it was. If territory could be expanded into, it was taken. These instincts were forged in scarcity and competition. They worked because the environment absorbed the consequences. A planet cannot. Earth is not an infinite backdrop. It's a closed system with slow feedback and delayed consequences. The moon shows what happens when feedback ends entirely. Mars shows what happens when it fails. Space shows what happens when there is none at all. This forces intelligence into unfamiliar territory. Choice without escape. To survive long-term, intelligence must develop a capacity evolution never required before. The ability to stop voluntarily, not because something is forbidden, not because something is impossible, but because something is harmful beyond a threshold. This is a radical idea. In human terms, it means recognizing when development becomes extraction, when efficiency becomes fragility, when power becomes risk. Saying enough is like loss. Enough energy, enough growth, enough acceleration. But in reality, enough is not an endpoint. It is a boundary that preserves motion inside it. Rivers that flood without restraint destroy their banks. Rivers that stay within them sustain life for millennia. Civilizations are no different. The hardest lesson intelligence must learn is that survival does not come from maximizing every variable. It comes from balancing many variables imperfectly over time. This balance be automated. Algorithms optimize, markets accelerate, technologies amplify. None of them naturally favor restraint. Restraint must be cultural. It must be taught, reinforced, normalized, and defended against short-term incentives. It must be respected even when its benefits are invisible. This is why endurance is rare. Not because physics makes it impossible, but because psychology makes it difficult. The universe does not tempt us. We tempt ourselves. The silence of space is not a taunt. It is a boundary condition. A reminder that the cosmos does not bend to desire. Stars burn whether watched or not. Planets erode whether inhabited or not. Time passes whether understood or not. Understanding does not grant exemption, grants responsibility. This responsibility cannot be deferred to future technologies or future generations. Delay is itself a decision, and decisions compound. A civilization that consistently delays hard choices will eventually face only impossible ones. This is the asymmetry of time. Early restraint preserves options, late restraint removes them. The moon had no chance to choose. Earth does. That difference matters. If humanity ever reaches a stable equilibrium with its planet, historians of the far future will not credit a single invention or discovery. They will credit a shift in values. A moment when the species learned that the greatest power is not expansion, but self-limitation. This idea runs against centuries of momentum. It will face resistance. It will be misinterpreted as weakness. It will be politicized. It will be delayed. But physics does not negotiate with delay. Every system has thresholds. Crossing them quietly is still crossing them. The narrow path forward is not heroic. It does not promise glory. It does not satisfy every desire. It promises continuity. Continuity of ecosystems, continuity of climate, continuity of culture, continuity of thought, and continuity once lost, cannot be reclaimed. The universe has no redo. The stars will not judge us, but they will not save us either. Only one force can do that: us. And whether we succeed will not be decided in space. It will be decided in how well we learn to say enough to have a fragile advantage. Why awareness changes everything. There is one advantage humanity possesses that no other force in the universe appears to have: awareness. Not intelligence alone, not technology, not curiosity. Awareness, consequence. Most systems in the universe operate blindly. Stars fuse until fuel runs out. Planets orbit until trajectories change. Ecosystems grow and collapse without foresight. Even evolution works through trial and error, discarding failures without memory. Humanity is different in one critical way. We can see outcomes before they arrive. We can model futures. We can recognize feedback loops. We can understand delayed consequences. This ability does not guarantee survival, but it creates a narrow opening where survival becomes possible by choice rather than accident. That opening is fragile. Awareness is uncomfortable. It forces trade-offs. It removes comforting myths. It demands action without certainty. Many civilizations may reach intelligence but retreat from awareness because it threatens existing power structures and short-term stability. Ignorance is easy to sustain. Awareness requires maintenance. Every generation must relearn it, reaffirm it, defend it against convenience. This is why awareness itself is a bottleneck. A species can develop technology faster than it develops wisdom. When that happens, awareness is a liability instead of a guide. Those who speak about limits are seen as obstacles. Those who push boundaries are rewarded, until the boundaries push back. The moon does not forgive. Mars does not forgive. Space does not forgive. Earth forgives, but only partially and only temporarily. This is the fragile advantage humanity still holds. We know what happens when atmospheres thin. We know radiation sterilizes worlds. We know how feedbacks lock climates into new states. We know how ecosystems collapse once diversity falls below critical thresholds. No previous civilization on Earth knew this in advance. We do. That knowledge changes the moral structure of the future. Collapse is no longer purely tragic. It becomes culpable. This does not mean blame. It means responsibility. Responsibility is the price of awareness. It is tempting to believe that someone else will act, that systems will self-correct, that technology will intervene just in time, that history always bends toward survival. History bends toward nothing. It records outcomes. The future will not judge intentions. It will inherit results. This is why space matters, even if we never colonize it. Space stripped away excuses. It showed us there is no cosmic abundance waiting to save us. No empty frontier to absorb mistakes. No second Earth prepared for handoff. The illusion of infinite fallback is gone. What remains is a single fragile biosphere and a species capable of understanding its limits. That combination is rare, possibly unique. And uniqueness does not grant immunity. It increases stakes. There is another reason awareness matters. It allows us to redefine success before failure forces the definition upon us. A civilization that defines success as dominance will eventually collide with limits. A civilization that defines success as stability has a chance to persist. This is not a guarantee. It is an opening. Awareness is not dramatic. It does not announce itself. It works quietly, often invisibly, through decisions that prevent disasters that never make headlines. No one celebrates the catastrophe that did not happen, but survival is built from absences. Absence of runaway collapse, absence of irreversible damage, absence of cascading failure. The moon is a world of absences. No air, no water, no life. Earth is a world of presence. That presence must be actively maintained. The universe will not intervene. The stars will not adjust. Time will not pause. Only awareness can guide action early enough to matter. This is why the greatest struggle ahead is not technological. It is cultural. Can a species value prevention over reaction? Can it reward restraint over spectacle? Can it treat long-term survival as success even when it feels invisible? These questions will decide whether awareness becomes humanity's greatest strength or its final regret. The universe offers no verdict in advance. It simply waits. And waiting is its most powerful weapon, the long responsibility. How a civilization learns to carry the future. If awareness is humanity's fragile advantage, then responsibility is its inevitable burden. Not responsibility in the abstract, not slogans or declarations, but responsibility measured in centuries, where decisions made quietly today shape realities no one alive will witness. This is the hardest scale for the human mind to grasp. We evolved to respond to immediate danger, to visible threats, to problems with faces and deadlines. The universe, however, operates on delayed consequences. Climate systems respond slowly. Ecosystems collapse gradually. Planetary thresholds are crossed silently before effects become obvious. This mismatch creates a dangerous illusion that nothing is wrong, everything is. A civilization that survives long enough must learn to act before proof becomes undeniable. Not because proof is lacking, but because waiting for certainty is itself a choice, and time does not forgive hesitation. The moon is the ultimate archive of this truth. It did not die suddenly. It lost protection slowly. Its magnetic field weakened. Its atmosphere thinned. Solar winds stripped what remained. Waters, what was once dynamic, became static. Not through catastrophe, but through neglect imposed by physics. Earth is not immune to this process. It is merely earlier in the story. Responsibility means recognizing that planetary systems are not resilient by default. They are resilient only within boundaries. Beyond those boundaries, recovery shifts from human time to geological time. And geological time does not care whether intelligence regrets its mistakes. This is why the future cannot be outsourced. Not to technology, not to markets, not to ideology. Technology can amplify decisions, but it cannot choose values. Markets optimize for incentives, not outcomes. Ideologies simplify reality, often at the cost of accuracy. Responsibility must be embedded culturally. It must exist in how cities are planned, how energy is produced, how food is grown, how risk is evaluated, how power is restrained, how knowledge is transmitted across generations. This is slow work. And slow work is vulnerable to impatience. Every generation inherits systems it did not design and consequences it did not initiate. This creates temptation to prioritize short-term comfort over long-term stability. The benefits of restraint are delayed. The costs of excess are postponed. This delay is central danger. Because once consequences arrive, they do not arrive gently. Climate systems do not negotiate. Biodiversity loss does not reverse on demand. Atmospheric chemistry does not care about intent. Responsibility, therefore, requires imagination. The ability to treat future humans as real stakeholders. The ability to feel moral weight for lives not yet born. The ability to act without applause. These are not natural instincts. They must be cultivated. A civilization capable of this undergoes a transformation more profound than any technological revolution. It shifts from reactive intelligence to anticipatory intelligence. Reactive intelligence responds to crisis. Anticipatory intelligence prevents it. Most civilizations never complete this transition. They react brilliantly. They innovate desperately. They recover temporarily, until one crisis exceeds their ability to respond. The silence of space may be filled with such stories. Worlds where intelligence emerged, flourished, expanded, and failed to restrain itself. Worlds where awareness arrived too late to alter trajectory. Worlds where the window closed quietly. If that is true, then the Great Filter is not a single event. It is challenge. Can intelligence remain aligned with reality long enough to matter? This alignment demands humility. Not cosmic humility, but operational humility. The acceptance that no model is complete, that uncertainty is permanent, that complex systems behave non-linearly, that control is always partial. Arrogance assumes mastery. Humility assumes vigilance. Humility does not mean inaction. It means caution paired with commitment. This is where many narratives fail. They frame restraint as fear. They frame caution as weakness. They frame limits as enemies. In reality, limits are the only reason stability exists. A planet with no limits becomes sterile. A civilization with no limits becomes unstable. The moon had no mechanism to protect itself. Earth does. That mechanism is us. Not as conquerors, not as owners, but stewards. Stewardship is not glamorous. It is repetitive. It requires maintenance, repair, monitoring, and adaptation. It demands constant correction rather than decisive victory. And yet, stewardship is the only role compatible with long-term survival. A civilization that embraces stewardship accepts that it will never finish its work. There is no final state, no permanent solution, only ongoing balance. This is psychologically difficult. Humans crave completion, endings, closure. But survival is an open process. It never concludes. The reward for success is simply continuation. Another century, another generation, another opportunity to choose wisely. The universe does not promise more than that, but does not forbid it either. The responsibility we carry is therefore not cosmic. It is local and absolute, to protect the conditions that allow awareness to exist at all, to avoid irreversible damage when alternatives exist, to treat the future as real even when it is silent. This is not a guarantee of survival. It is only chance. And chance, in a universe this hostile, is an extraordinary yet the final choice. What humanity decides to become. Every civilization reaches a moment when further progress is no longer a technical question. It becomes a question of identity. Not what it can build, not what it can reach, but what it chooses to preserve. At that stage, power stops being the central challenge. Direction becomes more important than capability. Without direction, power accelerates collapse. With direction, even limited power can sustain continuity. Humanity is approaching that threshold, not because it has conquered space, not because it has mastered energy, but because it has reached a scale where its actions shape planetary systems by default, whether intentional or not. This is the defining transition from species to planetary force. A force does not need intent to cause damage, but a civilization does. The moon stands as a silent counterexample. It is not hostile. It is not broken. It is simply complete. Its story ended early. Its surface preserves the past because nothing happens there anymore. No wind, no water, no cycles that renew. Earth is unfinished, and that unfinished state is not guaranteed. The decision humanity faces is not whether to terraform the moon, colonize Mars, or build orbital habitats. Those are expressions, not foundations. The real decision is whether expansion will be guided by responsibility or driven by momentum. Momentum is dangerous. Momentum carries systems forward even when direction is lost. It rewards speed over reflection. It punishes restraint. It transforms success into inertia. Many civilizations likely failed here. They mistook movement for progress. They confused growth with survival. They assumed expansion implied wisdom. Wisdom magnifies error. A mistake on a small scale is survivable. A mistake at planetary scale becomes irreversible. This is why the final choice is ethical, not technological. Will humanity define success as dominance or durability? Dominance is loud, durability is quiet. Dominance produces monument. Durability produces continuity. Dominance seeks control. Durability seeks balance. The moon could be dominated. Earth must be sustained. A civilization oriented toward dominance treats worlds as resources. It sees value in extraction, transformation, and utilization. This mindset scales easily. It is compatible with conquest, competition, and acceleration. But it has a terminal flaw. It assumes environments are passive. They are not. Every planetary system responds. Every intervention generates feedback. Every alteration creates unintended consequences. Dominance fails because reality resists simplification. Durability accepts complexity. It recognizes that systems cannot be fully controlled, only guided. That resilience emerges from diversity, redundancy, and restraint. That stability requires limits. This philosophy is harder. It requires slowing down when speed is available. It requires saying enough when more is possible. It requires maintenance instead of replacement. But ability works. It aligns intelligence with reality rather than fighting it. The future of humanity will be decided by which mindset becomes dominant within the culture itself, not by governments alone, not by corporations alone, not by scientists alone, but by the collective incentives that determine behavior. What is rewarded? What is punished? What is normalized? A civilization does not collapse because it lacks knowledge. It collapses because it fails to act on knowledge consistently. The moon teaches this lesson through absence. It shows what happens when protection is lost and renewal ends. Reminds us that planets do not recover on human timelines, that damage accumulates, that silence follows. If humanity chooses durability, its expansion into space will look very different from science fiction fantasies. Not cities everywhere, not rapid transformation of worlds, but careful placement of habitats, incremental adaptation, respect for planetary limits. Terraforming, if it ever occurs, will be rare. It will require overwhelming justification and extraordinary caution. It will not be the default. More likely, humanity will build environments rather than remake them. Artificial habitats, rotating worlds, controlled ecosystems, places designed for life rather than imposed upon it. This approach is slower, it lacks spectacle, but it preserves options. And preserving options is the core of survival. Once a planet is altered beyond recovery, the choice cannot be undone. Once an ecosystem collapses globally, restoration becomes theoretical. Once knowledge is lost, rediscovery may never occur. The universe does not offer refunds. The final choice humanity faces is therefore simple in structure and complex in consequence: to become a civilization that extracts until exhaustion, or a civilization that maintains until continuity. Neither path guarantees survival, but only one path, survival plausible. If humanity fails, the universe will not notice, the stars will continue, the galaxies will evolve, the silence will remain unchanged. But if humanity succeeds, something unprecedented persists. A self-aware fragment of the universe that learned to endure. A system capable of reflection and restraint. A continuity of thought extending beyond biological limits. This is not destiny, it is possibility. Possibility exists only in the present. Every decision that affects energy, matter, information, and life contributes to trajectory. No choice is neutral. Inaction is a choice. Delay is a choice. The moon has no choices left. For now, answer beneath the moon. When the last calculation is finished and the final argument is made, one truth remains uncomfortable and unavoidable. The universe does not care what humanity becomes. It does not reward effort. It does not punish mistakes out of justice. It does not guide civilizations toward wisdom. It simply responds to mass, to energy, to time. Meaning is not built into reality. Meaning is something intelligence must create and then defend. The moon reminds us of this with brutal honesty. It is not tragic because something was taken from it. It is tragic because nothing was ever guaranteed to stay. It existed in the right place, the right distance, under the same sun as Earth, and yet it became silent. Not through malice, not through failure, but through inevitability left unchecked. Earth stands at a different point on the same path. Alive not because the universe favors it, but because conditions aligned and persistence followed. That alignment will not last forever unless it is actively maintained. This is the central misunderstanding of intelligent species. They believe survival is the default state. It is not. Survival is an active process. Every stable system in nature survives because forces counteract forces. Feedback balances feedback. When those balances break, collapse follows not as punishment, but as consequence. Humanity, one of those forces, not an observer, not a passenger, a participant. This is why the future cannot be reduced to optimism or pessimism. Optimism assumes progress is automatic. Pessimism assumes failure is inevitable, both forms of surrender. The truth is more demanding. The future, conditional. It depends on restraint when power increases, on foresight when speed accelerates, on cooperation when fragmentation is easier. It depends on whether intelligence can outgrow its short-term instincts without losing its creative drive. The moon offers no warning signs, no alarms, no countdown. Outcome: a world stopped doing meaningful work. Earth has not reached that state. Life still cycles, water still moves, atmospheres still protect, magnetic fields still shield. But these systems are not permanent features. They are processes, and processes require continuity. This is where responsibility becomes more than a moral concept. It becomes a survival mechanism. A civilization that understands this does not rush to conquer the cosmos. It learns first to stabilize itself. It does not seek infinity, it seeks longevity. Expansion is not escape. Technology is not absolution. Knowledge is not immunity. Only alignment with reality sustains existence. If humanity succeeds, it will not be because it terraformed the moon or reached distant stars. It will be because it learned when not to act, when to preserve instead of replace, when to value continuity over novelty. The most advanced civilizations are not those that move fastest. They are those that last. And lasting requires something rarer than intelligence. It requires wisdom practiced daily, not admired abstractly. The moon will continue to circle Earth, unchanged, indifferent, silent. It will remain what it is. Earth, not. What Earth becomes depends on choices still being made. Quietly, incrementally, every day. There is no final triumph waiting, no moment where the work ends. Only the question that defines every intelligent species that reaches this point. Will awareness become stewardship, or will power outrun restraint? The universe will not answer. Humanity already is.